I will make a comparison between these two protocols. This is the outline for my presentation. Briefly, I'll have a brief background, 1 or 2 slides, and then I'll talk about the general formalism that these protocols are based on. The reference conditions has to be satisfied in order to perform reference dosimetry. The correction factors for the quantities needed to be used in doing absorbed dose calculation, practical implementations of the calibration procedures, and at the end, as mentioned earlier, I'll make a comparison between the TG51 and TRS 398. Some basic definitions here on what we mean by different reference dosimetry and radiation dosimeter. So reference dosimetry is basically the output calibration of clinical radiation beam by virtue of a direct determination of dose in water under specific reference conditions. And the radiation dosimeter is defined as any device that is capable of providing reading that is a measure of the dose deposited in the dosimeter sensitive volume by ionizing radiation. So we have 2 main categories of dosimeters. The first one is the absolute dosimeter that produces a signal from which the dose in its sensitive volume can be determined without requiring calibration in a known field. For example, we have the calorimeter and 3-key dosimeter, free air ion chamber. And for a relative dosimeter, these dosimeters that requires calibration of its signal in a known radiation field, like the calibrated chamber that used in these protocols, such as Farmer and parallel plate chambers. So these protocols provide methodology how to perform clinical reference dosimetry to ensure the uniformity and the accuracy of reference dosimetry in external radiation beam therapy. The TG51 protocol applied only to photons with cobalt 60 range to 50 MeV and electrons. Yet for TRS 398, it has even more calibration procedures for low energy photons and protons and heavy ions. This protocol based on usage of ion chamber calibrated in terms of absorbed dose to water. And the measurements is directly traceable to or by calibration factors obtained from primary standard labs or accredited calibration labs. What we mean by traceability, that if we have a radiation quantity and we measure that the absorbed dose from that radiation quantity, let's say 1 gray here, supposed to be the same value measured elsewhere, whether in North America or Asia, etc. So in other words, when we say that this chamber is traceable, or our measurement is traceable, that means it's calibrated in a primary standard lab or accredited calibration labs, such as what we have in our institution. So as a brief background, the old dosimetry protocols are based on exposure or air camera calibration factors of ion chamber in cobalt-60 beam. So the problem in these protocols that they are based on a calibration factor not related or is not directly related to the interested quantity that we are looking for. So that quantity is the absorbed dose in tissue. So it requires many correction factors, many conversion formulas to convert the air camera calibration factor to absorb dose to water. So that means it has inherent uncertainties, and they are complex and more prone to make errors in implementing these protocols. For the latest protocols, although they have been in the field for more than 20 years, they are based on absorbed dose to water calibration factor. So that means we're close to the quantity that need to be measured with dose in tissue, and they are more robust, more simpler, and less uncertain. They have less uncertainty than the old protocols. So talking about the general formalism, this is the main formalism which reference dosimetry protocols are based on for both photons and electrons. These two formulas are basically the same. It only requires the corrected reading and beam equality conversion factor and the absorbed dose calibration factors. So if we want to simplify our talking in a few words about the reference dosimetry, what we do exactly is we are performing, or we are positioning the chamber at a reference depth in a water tank. And after getting the reading of our radiation, we can convert that reading to dose. Okay. How to convert the reading at that depth to dose? We need something called calibration factor. How to get the calibration factor? So the same setup that we have earlier is the same setup we have earlier is done in the calibration lab. Okay, so the thing that in calibration lab, the dose at a reference depth is well known by the absolute dosimeter. Then by simply placing the detector in that reference depth, we can get the ratio of the dose over the reading of the detector or the dosimeter, and simply we can get the calibration factor for that detector. Then that calibration factor can be used in calculating the absorbed dose to water. Now, the first part of this presentation, which is reference dosimetry for photon beams. So let's talk about the reference conditions that has to be satisfied in order to perform reference dosimetry for photons. It has to be done in water, as stated in the protocols. The placement of the detector has to be on the beam central axis at 10 centimeter depth, and this is the reference depth for photon beam dosimetry. The field size has to be 10 by 10, whether we use the source to surface distance setup, SSD, so that field size has to be defined at the surface. And for source axis distance setup, SAD, that field size has to be defined at the reference depth or the measurement depth. So this is illustrating the two setups. For SSD setup, the reference depth is 10 cm and the field size is defined at a water surface, and the SSD is in here is 100 cm, supposed to be 100 cm from the source. And for the SAD setup, the distance is 100 cm as well. The reference depth in water is 10 cm, and the field size is 10 by 10, but is defined at the dosimeter level. What the equipment needed to perform the reference dosimetry? We need a calibrated ion chamber and electrometer, which has an NDW factor, calibration traceable to standard laboratory. We need waterproofing for ion chamber if needed. If our ion chamber is not waterproof, it has to be waterproofing has to be less than 1 millimeter thickness of MMA. The measurement has to be done in a water phantom. So we need a water phantom which has dimensions at least 30 by 30 by 30 centimeter cube to provide enough back scattering and lateral scattering. It requires also a 1 millimeter lead foil for photons, for photon beams above 10 MeV and above. And we need a system to measure air pressure and water temperature. It has to be as well calibrated. Back to general formalism. So the absorbed dose to water equals the corrected meter reading M multiplied by the beam equality correction factor KQ multiplied by the absorbed dose to water calibration factor at cobalt 60 beam or any beam equality that used in calibration lab. Mainly we have in the calibration lab, they use cobalt 60 beams. Very rare in the calibration lab, they use X-ray reference beams or electron beams. So if here we talk about the beam equality conversion factor, KQ, this factor is Monte Carlo driven or Monte Carlo derived factor, which is basically the derived from the ratios of stopping power ratio, water to air, for the user beam equality to that one of cobalt 60 beam multiplied by the perturbation parameters that affect the fluence of the measured beam. So if we go to each one of them, so the first factor here, we have the first, the stopping power ratio, water to air, whether for the user beam equality and for the reference beam equality, the cobalt 60 beam. Then the second one is the correction factor that account for the gradient at the point of measurement. It's only for a cylindrical chamber because the one for parallel plate chamber is equal to 1. Then the fluence correction factor that correct for the presence of the cavity, the perturbation happen on the electron fluence because of the placement of the cavity, the air cavity. And then P wall, that accounts for the differences between the differences in photon mass energy absorption coefficient and the electron stopping power ratio of wall material and medium. And the last perturbation factor is the central electrode correction factor, which accounts for the lack of air equivalence of the central electrode. So how to find or determine KQ? Yet we didn't, it's not possible to calculate all of these factors while doing reference dosimetry. These protocols provide a methodology to get the beam equality specifier, to get the beam equality factor, correction factor. That methodology based on the beam equality index, which in case of, for the case of photons, we have it percent depth dose at 10 cm for the photon component only. And for low energy photons, which is below 10 MeV, 10 MV, the measured percent depth dose at 10 cm is equivalent to the beam equality specifier, the percent depth dose at 10 cm for photon component only. So electron contamination has to be accounted for, has to be removed. But for low energy photons, the electron contamination is negligible. For high energy photons, in order to get the percent depth dose at 10 cm from photon component only, we have to measure the percent depth dose while placing a 1 millimeter foil at a 50 cm from the surface, from the water surface, and measure PDD. So that PDD called the PDD for lead. And then the protocol provide us with the equation to convert the PDD at 10 cm for in case of a placement of lead foil to that one that for the machine for the photon component only. And it's also provide us with alternative method how to get the beam equality specifier using the measured PDD without lead foil using this equation. Okay. So since we're talking about the measurement of percent depth dose in water, this protocol also define the point of measurement, how to place or how to position your detector, your dosimeter in water in order to measure the PDD and to make a reference dosimetry. So in case of the cylindrical chambers, the placement of the placement of the detector is referred to the central axis of the chamber in case of cylindrical chamber. Yet the effective point of measurement is at the shallower depth, closer to the source. Depends on the type of beam that we are performing calibration. And for parallel plate chamber, the point of measurement is at the front surface of the air cavity, and the effective point of measurement is also at that point. So the position of parallel plate chamber is the same at the same point of effective point of measurement. But for cylindrical chamber, the placement of cylindrical chamber is at the central axis, and the effective point of measurement is going to be provided in the next slide. So for cylindrical chamber, the effective point of measurement is equivalent to the depth of measurement minus 0.6 R cavity minus 0.6 the radius of the cylindrical chamber for photons. And the effective point of measurement in electrons is at a 0.5 R cavity, closer to the source or the beam source. And as we said, that for parallel plate chamber, the effective point of measurement is at the front surface of the air cavity or the inner surface of the front window. So to measure the percent depth dose here, we said we place the chamber at the point of measurement, which is the central axis of the chamber. Then after measuring PDD, that curve need to be corrected for the effective point of measurement. And the effective point of measurement, we said that it's at a 0.6 R closer to the source. So the whole curve has to be corrected or shifted by 0.6 R in order to get the percent depth dose of the photon beam. And for high energy beams, another measurement or percent depth dose measurement need to be performed in order to get the beam quality specifier. So the first percent depth dose needed for the reference dosimetry. The second percent depth measurement with a lead foil is needed for the beam quality specifier. So the placement of lead foil is done for the removal to remove the electron contamination, and from that curve we can get the PDD at 10 cm that's required to get the beam quality specifier for that beam. After getting the beam quality specifier, the protocols provide tabulated values for KQ. Here we have a figure that shows the KQ values against the beam quality specifier for several commercial cylindrical and parallel plate chambers. Sorry, the parallel plate chamber is not recommended to do reference dosimetry for photons. It's only cylindrical chambers. And also here for the some of cylindrical chambers are not the KQ values are not given in the old TG51 or the TG50, the original 51 protocol, are given in the TG51 addendum. And even for the KQ values that for the chambers given in the original 51, we have them here with slightly different or slightly corrected values. And here the addendum also provide a formula how to calculate the KQ from the PDD, from the beam quality specifier PDD 10. Then we have the the charge measurements, the measurement by our detector, has to be corrected for many influences parameters. So the measurement we get from our chamber considered as an uncorrected charge reading. It has to be corrected for the saturation effect, the changes in the air mass, the polarity effect on the measurement. So we should go to each one of them one by one. The first one, is the electrometer calibration factor or correction factor, which is correct for the electrometer if it's not calibrated with ion chamber. Most of our electrometers usually calibrated with the ion chamber. So the correction factor for the electrometer is considered as 1 in that case. The second correction factor, the ion recombination correction, it accounts for the inefficiency in collecting the charge that generated in air cavity of ion chamber. It uses 2 voltage method, the high voltage, the normal operating potential or voltage, and the reduced potential value. So the ratio between these potentials or values has to be 3 or more. And then we get the reading for the normal operating potential and the reading for the reduced potential, and we can get the recombination factor, correction factor. The third correction is the polarity correction. We all know that the reading of the chamber differs when we flip the polarity of the polarity applied on the chamber. So this formula is basically taking the mean value of the chamber reading for both polarities. The fourth correction factor is the pressure temperature correction, which account for the changes in the air mass inside the air cavity of ion chamber. Since the calibration environmental conditions is slightly different from the environmental condition we have in our institution or in the machine environment. So usually the calibration lab maintain a temperature of 22 Celsius in North America, or 20 Celsius in Europe, and the pressure is 101.33. So having different environmental conditions will affect the mass of air inside the cavity. So it will affect the accuracy of the charge collected and our measurement, and it has to be corrected. So the temperature here is given in Celsius and the pressure in kilopascal. So by this, we end the dosimetry for photons, and we can move to the reference dosimetry for electron beams. Shall I continue, or? Dr. Walid, can you hear me? Hello? Hello? Hello, can you hear me? Hello?
Yeah, Mahmoud, we can hear you, but
Okay.
I'm not sure if, I mean, I would suggest you continue
Okay.
because it's work. I mean,
Okay, I'll continue. So here now we have the second part of this presentation on reference dosimetry for electron beams. So generally, the setup is very similar to that one of photons, yet there are few differences. So for the field size that needed to be used for electrons, it has to be 10 by 10 at the water surface. Here for electrons, only allowing SSD setup. And that 10 by 10 field size at the water surface is only for for electrons that has a beam equality less than 8.5 cm. That means less than 16 MeV electrons. And for electrons that has energies higher than 16 MeV, the recommended field size is 20 by 20. And for us, as the distance between the water surface to the source, it's recommended or it's more flexible for electrons. You can use SSD from 90 to 110 cm, but you have to make your output factor based on, you have to fix your SSD and make your output measurement, whatever, based on that distance. For the reference depth, we have a formula that provided by the protocols, which is 0.6 R50 minus 1. That's where you place your chamber when doing calibration for your electron beam. It has a reason why they select that depth, that reference depth, since the stopping power ratios for electrons varies with depth. It's reducing with depth. So they found out that the stopping power ratio at that point for various Linux is almost constant or can be fit in one curve. So the uncertainty in calculating the stopping power ratios or the uncertainty in chamber calibration factor is minimal at that point. So that's why they selected that point in performing calibration for electron beams. That reference depth is very close to Dmax for low energy photo electrons, which is below 10 MeV, and slight and deeper than Dmax for higher electron beams. And as we said, the position of the detector depends on the type of detector you're using. In case of using cylindrical chamber, it has to be placed at the central axis of the detector. And in case of using the parallel plate chamber, it has to be positioned at the front face of an air cavity. And the general formalism for calculating absorbed dose in water is basically the same as the one of photons, yet in TG51 protocol, they break down the factor into specific values or quantities. They have moved out the gradient correction factor, and they came up with so KQ here is equivalent to the gradient factor multiplied by KR50, and KR50, which is the electron quality correction factor, is equal to KR50 prime to Ka cal. We'll explain these quantities later, and we end up with this formula at the bottom, similar to the one we have in photons, except the differences we have to how to calculate the beam quality correction factor. So similar to the photon beams, this quality correction factor, it accounts for the differences in the stopping power ratios between water to air, the medium to the medium of the ion chamber, the medium of measurement to the medium of the ion chamber cavity, which is air, multiplied by the influences parameter or perturbation parameters I explained earlier. Then if we get out the gradient correction factor, will become KR prime, KR50. And all of these values are Monte Carlo generated ones. Then they split the KR50 into two factors, the KR50 prime and Ka cal. And I'll be explaining all of these quantities in the next slides. So let's take the Ka cal. Ka cal is called as the photon electron conversion factor. So TG51 wants to remind us that the calibration factor that we're using in our reference dosimetry is generated or is calculated based on radiation in the chamber on a cobalt 60 beam and a photon beam, which is different from electron beam in terms of type, the beam type, and energies. So by getting this quality conversion factor Ka cal, you convert the calibration factor, absorb those to water calibration factor for photons to an arbitrary correction factor for, sorry, not arbitrary correction factor, for a correction factor for an arbitrary electron beam quality. So multiplying the absorbed dose correction factor for your chamber by Ka cal, you give a calibration factor for your chamber for arbitrary electron beam quality Ka cal. And it's a chamber specific. So we have values, tabulated values in TG51 for Ka cal. And it's not dependent on the user beam quality, since it only rely on an arbitrary beam quality, electron beam quality, QE cal. Okay. So this basically the factor that account for correction beam quality from photon to electron. And the next or the other quality conversion factor is called as electron quality conversion factor, KR50 prime, which corrects the calibration factor from the arbitrary electron beam quality QE cal to the user electron beam quality Q. And also the values for for KR50 prime is available in the protocols. And can be also calculated using the expression here for both cylindrical and parallel plate chambers. So this figure from TG51 protocol, we have different figures for parallel plate chambers and for cylindrical chambers. So we can get the KR50 prime against if we have the R50 values for our beam quality. So how to get the beam equality correction factors? We collected it through the beam equality specifier for electrons, which is the R50. R50 is basically the depth which dose falls to 50% of its maximum value for field with full side scatter, and can be calculated from the depth ionization curve at 50% of its maximum value. So that means we need to measure the depth ionization curve in the beginning. So we measured using our cylindrical chamber or our plane parallel chamber, parallel plate chamber. Okay. So in case if we measure the percent depth ionization using the cylindrical chamber, and
Mamoon,
yes,
you have 5 more minutes. We have a good number of questions, so we'd like to leave some time for the Q&A, please.
okay. So quickly here, we can measure the percent. Firstly, we measure the percent depth ionization curve using our cylindrical chamber, and this, as we said, that the point of measurement is at the central axis of the chamber, has to be corrected by 0.5 R cavity to get the corrected depth ionization curve. Then for parallel plate chamber, no need to shift the curve. And after shifting the curve, we need to correct the values, the depth ionization curve to depth dose curve into applying the stopping power ratios for electrons at different depths, which is provided by TG25. Because the variation of the stopping power ratios. Then as a summary, we can measure depth ionization curve. We shift the effective point of measurement for cylindrical chamber, and for diodes and parallel plate chamber, no need to shift. And actually, if we have, if we're measuring percent depth dose with diodes, no need. The measured values are directly considered as a percent depth dose. Then we convert the percent depth ionization to percent depth dose using TG51 values. And the last correction factor, we have it here, the gradient correction, since they focus or they maintain the position of the chamber for both depth dose measurement or reference dosimetry. So the gradient effect has to be accounted for by this value. You have to maintain the position of the chamber, the central point of measurement, the central chamber position at the reference depth, and then you do gradient correction. Then we have the same formula, and we can correct for the chamber reading, similar to the correction we have in photon beams. This is cross calibration. So as a summary, we measure for photon beams, we measure PDD with a lead PDD 10, and we insert the lead foil in case if we have photon energies more than 10 MV, and we can determine our beam quality specifier PDD 10 for getting KQ, and then we measure, we get the reading, and we correct that reading for correction factors. Okay, in case of temperature, pressure, polarity correction, ion recombination, we can get KQ value for that beam using the beam quality specifier. In case of electrons, similarly, we can, after having, okay, by default, we have a calibration factor for the chamber used in calibration. We measure percent ionization depth curve and determine R50. We shift the curve. We get the reference depth. We do the measurement at the reference depth, and we correct that measurement. And we have from R50 we can get from the type of chamber that used, we can get K cal, and from R50 we can get KR prime, and we measure the gradient correction factor in case of using cylindrical chamber, and then we can calculate absorbed dose. So now the last thing I want to say here, the comparison between two protocols. In TG51, it's only for high energy photons and electrons, and for TRS it includes also low medium energy KV photons, cobalt 60 high energy photons, and protons and heavy ions. The beam quality specifier for TG51 is depth dose, percent depth dose at 10 cm for photon component only. For TRS, the beam quality specifier is TPR 2010, and many users, they use alternative method, which is much simpler to get TPR 2010 using the PDD 2010. And in case of electrons, the point of measurement at the reference in TG51, the point of measurement is at the reference depth, which is the central axis of the cylindrical chambers. Parallel plate chamber usage is preferred below 10 MeV, must be used below 6 MeV. The cylindrical chamber can be used above 6 MeV. Only water phantom allowed in the measurement. We have tabulated values for Ke cal and KR50 prime to get KQ factor. For TRS 398, the restaurant depth for parallel plate chamber at the point of measurement, which is below the inner at the inner surface of the detector. For cylindrical chamber, the reference point of the cylindrical chamber is at effective point of measurement, not at the central axis of the chamber. Parallel plate chamber is recommended for all electron energies, but must be used below 10 MeV in that protocol. So the cylindrical chamber cannot be used, or they don't recommend to use it at all in below 10 MeV. It's only can be used above 10 MeV. Plastic phantoms are allowed for electron energy below 10 MeV. And the last thing is they don't split the KQ factor into Ka cal and KR50 prime. They have only tabulated value for KQ for electron beams. Can be get from the beam quality specifier R50, similar to TG51 as well. So, and here there's a paper. They made a comparison between these two protocols, and they found out that the maximum difference you can get is 0.6%. Thank you so much.
Thank you, Ma'moon.